Lecture 5, Trees and Distance. Preface, recap of previous lecture. In previous lecture, we have discussed the application of Eulerian circuit, that is the Chinese postman problem and its algorithm. We have seen. We have also seen the degree sequence, then graphic sequences and two switch operations, and the theorems based on the graphic sequence we have also proved in the last lecture. Content of this lecture: in this lecture we will discuss the basic properties of a trees and the use of distance in the tree and the graph. So, basic properties of a tree means we are going to basically introduce a theorem which will characterize a tree. So, let us start looking at the basic properties of a tree. The word tree suggests branching out from the root and never completing a cycle. So, the trees as the graph have many applications, especially in the data storage applications, searching of a data, and in the communication network. These trees are going to be very useful. Definition: a graph with no cycle is acyclic. A forest is an acyclic graph. A tree is a connected acyclic graph. You can also say a tree is a connected forest. Why? Because forest is also an acyclic graph. So, a tree is a connected forest, or you can also say a tree is a connected acyclic graph, or the tree is a graph which is not having any cycle and also it is connected. Then one more element is introduced in the tree for our discussion, that is called a leaf or a pendent vertex. Leaf or a pendent vertex is a vertex of degree 1. Let us see the example over here. So, as far as forest is concerned, forest is an acyclic graph. So, here we have given two different acyclic graphs and that constitutes a forest. Now, when we talk about the tree, so tree is a connected acyclic graph. So, this particular component which is a tree, here you can see that it is connected, that means all the nodes are connected via an edge and there is no cycle also. So, it is a connected acyclic. So, tree is a connected acyclic graph. Now, within this particular tree, a node which is called a leaf node has the vertex degree of 1. So, here this is also a leaf node, this is also a leaf node. So, we have seen three definitions. One is the forest. The property is that it is basically an acyclic graph, that is all, which is not necessarily connected. Now, tree is a connected forest. So, that means can also say it is a connected acyclic graph. Similarly, in a tree or in a forest, the vertex with a degree of 1 is called a leaf node or a leaf vertex, or it is also called a pendent vertex. So, all these things we have seen here as part of the definitions in the background. Spanning subgraph. Spanning subgraph of a graph is a subgraph with a vertex at Vg. That means a subgraph which includes all the vertices of a graph is called a spanning subgraph. A spanning tree is a spanning subgraph that is a tree. So, take this particular example, this is a graph G, and if we include all the vertices and basically some subset of the edges, then it is called basically a spanning subgraph. Now, if we take the subset of this particular graph which includes all the vertices of a graph, but only those particular edges of a graph which will form a tree, then it is called a spanning tree. A spanning tree is a spanning subgraph that is a tree, that is called a spanning tree. Now, tree is a connected forest. This particular definition I have already given you, and every component of a forest is a tree, that also I have stated. So, a graph with no cycles has an odd cycle, has no odd cycle, hence trees and forest are bipartite graph. So, bipartite graph are characterized by the property that they do not have any odd cycle, since the graphs, since the tree do not have any cycle, hence it does not have the odd cycle, hence the trees are and the forest are the bipartite graph. Paths are the trees. A tree is a path if and only if its maximum degree is 1. So, you can see this is the path. So, this becomes a tree. Why? Because it is a connected acyclic graph. This tree is also a path if and only if the maximum degree is 2. So, if you include a vertex, then it is not a path, but it is a tree. So, this is not a path. Path says that, why? Because here the degree of this node is more than 2, hence it is not a path. So, therefore, a tree is a path if and only if its maximum degree is 2, that we have already checked and seen. A star is a tree. Star is a tree consisting of one vertex adjacent to all other going away from that particular, going out from that particular vertex is called a star. N star is represented in a form of a bicyclic, that is k1 comma n minus 1 other vertices. Now, the graph that is a tree has exactly one spanning tree. This is important. The full graph itself, the spanning subgraph of G need not be connected, and a connected subgraph of G need not be a spanning subgraph. For example, if the number of nodes in a graph is greater than 1, that means let us assume it is having the 2 nodes, then empty subgraph with a vertex at Vg and edge set phi, there is no edge here in this example, is a spanning subgraph, is a spanning but not connected. So, a spanning subgraph not necessarily be connected. The other condition says that, and a connected subgraph of G need not be a spanning subgraph. For example, let us assume the order of the graph is greater than 2. So, greater than 2, let us say that it has 3 different vertices. The order of the graph is now 3, and 2 of them is having an edge. So, this is a graph. So, this is a connected subgraph of a particular graph G. It need not be a spanning subgraph. So, this is portion is connected, but this portion is left out. So, this particular portion is called a connected subgraph of the entire graph G. but it need not have to be a spanning subgraph, because this node is left out, hence it is not a spanning subgraph. So therefore, when we talk about a spanning subgraph, then we have to mention whether it is connected or not. If it is a spanning subgraph which is connected, then it will form a tree. Spanning acyclic connected subgraph is a tree. So Cayley's formula gives you about how many different possible trees you can construct out of n nodes. So if there are n vertices, then you can construct the trees including all the vertices, spanning all the vertices, hence those trees are called spanning trees. So with n vertices you can construct how many trees? N raised to power n minus 2 trees on the vertex set of n. So this particular formula is called Cayley's formula. Let us take the example. Let us take the example when it has 3 different vertices. If it has 3 different vertices, you can form 3 different spanning trees in this way. If these 2 edges are connected, these 2 edges, these 2 vertices are connected by an edge, or these 2 vertices are connected by an edge. This is 1, 2 and 3. So by Cayley's formula, if we say n is equal to 3, then 3 raised to power 3 minus 2, that becomes 3 raised to power 1, that is 3 different trees. And this is an example which has illustrated. Now when you have 4 different vertices given, then there are 16 possible trees according to the Cayley's formula. We can see all these 16 different possibilities. Which are stated here. Then there is a lemma which is stated as every tree with at least 2 vertices has at least 2 leaves. Then another portion says that deleting a leaf from an n vertex tree produces a tree with n minus 1 vertices. Let us see the proof of it. Now a connected graph with at least 2 vertices has an edge. Now in an acyclic graph, an endpoint of a maximal non-trivial path has no neighbors other than its neighbors on the path. So the maximal path, if we consider, then in that particular path these 2 vertices are basically the leaf nodes, and hence a cyclic in an acyclic graph, that is a tree with at least 2 vertices has at least 2 leaves. For example, if let us say assume that at least 2 vertices, let us assume that the vertices are, total number of vertices is 3 and 2 are the leaf nodes, and there is one more node available. So if you place an edge, how many edges will be there to form a tree or a cyclic graph? Is required only 2 edges. Now if we place further more edges like this, then the nodes at the end, they are called basically the pendant vertices or a leaf node, will have the degree more than 1, and there will be a back edge, and this back edge will be connecting some node in the maximal path, for example this node, and thus it will form a cycle, and which is contradicting that it is basically a tree which is an acyclic graph, so that is not possible. Furthermore, when we talk about a maximal path, that means 2 nodes which are farthest apart, this particular maximal path cannot be further extended. Why? Because this is the maximal, that is why it cannot be contained any other maximum path, and that is why it is maximal, cannot be extended further. If let us say it is having an edge, then it is go and join the particular already existing vertex in the maximal path, and it will form a cycle, which we have seen it is not possible. Hence the endpoints of such a path are basically the leaf nodes. Now we have to see the other part of the proof, that deleting a leaf from an n vertex tree will produce a tree with n minus 1 vertices. Now let V be a node of a graph which is basically a leaf of a graph G, and this particular leaf node means it has the degree is equal to 1. Why? Because this is a pendant vertex, property of a pendant vertex. So that means there is one edge which will connect to some node in the remaining part of the graph. Let us call it as G prime. So we can define G prime as G minus this particular vertex. If we remove, this will be the G prime. So a vertex of degree 1 belongs to no path connecting the two vertices. So if there are two vertices, let us say U and W within G prime, so it cannot come in between. Why? Because it is a pendant vertex, its degree is 1. So any other vertex between U and V must have the degree more than 2. Hence V cannot be the node within any connected set pair of vertices within G prime. Hence all the pair of vertices, they have a path, connecting path within it. Therefore G prime is a connected graph. Since deleting a vertex cannot create a cycle, therefore G prime is an acyclic. Why? Because the original graph G is a tree which is an acyclic graph. So if you remove a vertex out of a G, the remaining graph will also be acyclic. So it is a connected, it is acyclic. So therefore G prime is a tree, but here the number of nodes is n minus 1 in contrast to G which is having n nodes. So hence the statement is proved. So we started with a graph, we started with a tree which is a graph. So every tree has at least 2 leaves that we have seen in the previous theorem, and if we take out of these at least 2 one leaf, let us say V, and if we remove it from the graph, the resulting graph is G prime. So G prime is also a tree with n minus 1 vertices that we have already proved. So this particular lemma will implies that every tree with more than one vertex arises from a smaller tree by adding a vertex of degree 1. So this is how we can expand or we can construct a tree from a single node vertex. In the next slide we will be seeing the equivalence, and that basically equivalence of trees, that is the characterization of the trees, and we will be using different methods of the proof, that is called induction. Prior results also is used, then counting arguments, extremality and contradiction. All these methods of different proofs we are going to see here when we look upon the characterization of the trees. Characterization of the trees, there is a theorem which states that for n vertex graph where n is greater than or equal to 1, the following are equivalent, and also will characterize the tree of n vertices. So following are equivalent and they will characterize the tree in the sense, when we say that G is connected and has no cycles, this will define as the tree, and that is also equivalent as another definition of a tree, that G is connected and has n minus 1 edges. This also will characterize a tree. G has n minus 1 edges and no cycle will also characterize a tree. G has no loops and has for each UV pair within the vertex set of G exactly one UV path exists, then it will also characterize a tree. So all these 4 different statements or properties they will characterize a tree and they are all equivalent, that we are going to prove now. So, proof: the first, we will demonstrate the equivalence of A, B and C by proving that any two of these three A, B, C properties, they will basically represent the properties, three different properties connected, cyclic and n-1 edges. So, out of these three, if we pick any two in any of these properties, then it will imply the third one, and that is how the equivalence of ABC will be proved. Let us see the first theorem. So, this particular theorem has 4 different sub theorems or 4 different theorems, which will comprise of this bigger theorem. So, the first theorem says that A means if a graph G is connected and has no cycles, then this will be equivalent to the properties B and C. So, B and C also has connected and n-1 edges, n-1 edges and no cycles. So, basically n-1 edges was not there in A. So, that means connected and acyclic will basically imply that it has n-1 edges. Let us use the induction on n. For n is equal to 1, a cyclic one vertex graph, how many edges are there? No edge. Hence, this particular statement, that is having n-1 edge, is basically satisfied. Why? Because 1 minus 1, that becomes 0, and how many edges are there? There are no edge when n is equal to 1. So, this single vertex node is connected acyclic, and now it will be having n-1 edges. Now, if n is greater than 1 and we suppose that implication holds for the graph with the fewer than n vertices. Now, given an acyclic connected graph G, that is the statement that we are given. If we apply using lemma 2.1.3, here we are provided with a leaf node. Why? Because every connected acyclic graph G, that is a tree, will have at least 2 nodes with a degree 1. So, let us assume a leaf node with a in this particular graph, and also that particular lemma will state that if we remove it, then the resulting graph G prime is also acyclic and connected. Now, by applying the induction hypothesis, which assumes that with the fewer than n vertices, this particular condition holds. So, basically for G prime, this condition holds, means G prime has n minus 1, n is n minus 1 minus 1, that is n minus 2 edges it has. So, that is what we have written over here. Now, since V is a vertex which was there in the original graph, so let us count how many edges will be there in our original graph, knowing that G prime is the graph which has n minus 2 edges when we plug in, and the degree of this particular leaf or a pendant is 1, that we know if we plug in. So, the total number of edges in the original graph comes out to be n minus 1. Hence, this particular part of the theorem we have proved by induction. Now, the second property, the second part of the theorem says that B is the condition that if it is connected n minus 1, so we are going to show that it is having no cycles, that is equivalent to no cycles. So, let us assume that the graph G which is given to us is connected and has n minus 1 edges, and we have to prove that this will imply that it is acyclic. Now, let us prove it by the contradiction. Suppose if this particular graph is not acyclic, suppose this graph is not acyclic, then we can delete the edges from this particular cycle. So, we can delete some of the edges, either this edge or the other edge. So, we can delete the edges from the cycle of G one by one until the resulting graph, that is called G prime, becomes acyclic. So, that means if a graph which is not acyclic, we can convert it to a cyclic graph by removing some of the edges, deleting some of the edges. Now, you know that no edge on the cycle is an cut edge. That particular characterization we have seen in the earlier slides. Therefore, G prime is connected by the theorem. Why? Because it is not deleting the cut edges, but it is deleting the edges out of the cycles. Hence, by theorem 1.2.14 that we have seen earlier lectures will state that removing the edge from the cycle will not disconnect the graph. Why? Because they are not the cut edge. So, from the above implication, it implies that the number of edges which are present in G prime. Why? Because G prime is connected and also it is acyclic. We have made it acyclic, it was also connected. So, it has n minus 1 edges, because we have done through this operation. Now, we are already given that the graph G has n minus 1 edges, and we have basically obtained, so that was given to us. Here, and but by this particular step we have achieved a graph G prime, and that is by deleting the edges, and the total number of edges which are there in G prime is also n minus 1. So, how many edges we have deleted? We have not deleted any edges. If no edges are deleted, that means both the graphs are same. Since we assume that our graph is basically this G prime is acyclic. Why? Because we have obtained the acyclic graph by edge deletion. Since no edge is deleted, so G prime is acyclic, hence G is also acyclic, hence we have done the proof. Now, third part, which says that G has n minus 1 edges and no cycles. That means we are going to prove AB. AB has this particular condition that it is also necessarily connected. If it has n minus 1 edges and no cycles, that means it will be connected. Now, let us see the proof of it. So, the proof here we are using the counting. So, let us see that G graph which is given to us has k different components. Some are small, some are big. So, 1, 2 and so on up to k different components in graph G. These components we can write down G1, G2 and so on up to Gk. Now, since every vertex appears in one of these, for example, if it is V1, V1 cannot appear in any other component. So, here V2 will appear, here V3 may appear, here V4 may appear and so on. So, every vertex appears in one of the components. So, let us count how many vertices will be there total. So, we will count the number of edges in the component Gi, and we sum over all I from 1 to k. So, the total number of vertices in this way becomes n for an n vertex graph. Now, another thing which we have to see is that since it is given that G has no cycles, So, each component will satisfy the property. What is that property? That every component is connected. So, it will be having how many different edges. So, every component will have this n minus 1 different edges. So, let us count these number of edges also 1 to k. So, that becomes the summation of, you know, that E of G I, the number of edges in a particular component is n of G I minus 1, and this particular summation will go from I is equal to 1 to k. So, here this particular factor will introduce k, and this factor is already known as n. So, the total number of edges here will be n minus k. Now, we are given that this particular graph has n minus 1 edges, and we have counted that it becomes n minus k. So, n minus k, when you make equal to n minus 1, this implies that k is equal to 1. So, if the number of component here we have assumed it is k, if it is 1, then the graph is connected. Hence, by if the graph has n minus 1 edges and no cycles, we have concluded that this particular graph must be connected. Now, the next part of this particular theorem says that if the graph which is given is connected and no cycle, this will imply that for any pair of vertices of a graph, there is only one and one path exists. That means there is exactly one path for every UV which is there in the vertex set exists. That we have to prove it. Now, since graph G is connected, that is given. So, each pair of the vertices is connected by a path. This is the definition of a connectivity which we have seen earlier. So, for example, if this particular graph is connected and for any two vertices, let us say u and v, they are basically having a connection through a path. So, if some pair is connected by more than one such paths, so we choose the shortest, that is the total length shortest path, a pair, let us say p and q, there are two shortest path exist of the distinct path with the same endpoints. So, with this extremal choice, extremal in the sense all other paths we have ignored, only the shortest one we have considered, and incidentally let us say there are more than one shortest path. So, we have now seen the extremal conditions. So, we are looking the extremality condition here in the proof. So, by this extremal choice, no internal vertex of P or Q can belong to the other path. So, this implies that P union Q will form a cycle and which contradicts the hypothesis A, which basically assumes that the graph is connected, but it does not have any cycle. Hence, this particular assumption that it is connected by more than one such paths, this also is contradicted. Hence, it is connected by exactly one path. The last part of this particular theorem says that D, the statement of D says that for any pair of vertices in a tree, there is exactly one UV path exists, and this will imply that that particular tree is connected and having no cycles. Let us see the proof. Now, if there is exactly one UV path for every UV, then basically u and v is connected. Let us assume that it contains a cycle, and we are going to prove by contradiction. Let us assume there is a cycle in G here, then G has two UV paths. This is one path, this is another path between U and V, and that will go around this particular cycle will provide two different paths. Hence, the G is acyclic. Why? Because the statement of this particular theorem opens with the condition that it has only one UV path. Now, with the two UV path, if a cycle exists, then it will be having two UV path, and hence this particular condition will be violated. Hence, by contradiction, it has only one path. If it is one path, then it is acyclic. It is connected also. Why? Because this path will provide the connectivity, and it will forbid or it will ignore the condition that it will be having a cycle. So, it is a connected graph. Why? Because the paths exist between any two pair of vertices. And there is no possibility of a cycle. This will conclude that both our conditions are basically satisfied. So, this is equivalent to saying that if, let us say, there is exactly one path exists between U and V. So, basically then the graph will become a connected, and also the graph will become acyclic. So, there are some corollaries based on this particular theorem. Let us see those corollaries quickly. Now, every edge of a tree is a cut edge. This is quite obvious in the proof. Now the tree has no cycles because it is an acyclic. So, the theorem says that every edge of a tree is a cut edge. Why? Because there is no cycles. So, all the edges of a tree will not lie on the cycles. If they are not lying on the cycle, then every edge is a cut edge. The other corollary which says that adding one edge to a tree will form exactly one cycle. So, tree has the unique path linking between every pair of vertices in the previous theorem which we have seen through the D condition. So, joining any two vertices by an edge will create exactly one cycle. So, here if you join any two vertices by an edge, it will create a cycle, and that will be exactly one cycle which will be created. Third part of a proof says that every connected graph contains a spanning tree. So, as in the proof of the property B which we have seen in theorem 2.1.4, that we considered a graph and iteratively we were deleting the edges till the graph becomes acyclic. So, by deletion the edges, the subgraph which we obtain is a spanning subgraph which is connected and which is acyclic. So, the connection was already given the condition. So, that means when we delete all the edges from the cycle to make it acyclic, so it becomes an acyclic graph. When we delete the edges, that means we are not deleting the vertices, the spanning subgraph it is. So, spanning subgraph which is connected and acyclic, which we obtain, is nothing but a tree. Proposition: if T and T prime are the spanning trees of a connected graph G, and there exists an edge which is present in T but not present in T prime, then there is an edge E prime which is present in T prime but not in T, such that T minus E plus E prime is a spanning tree of G. So, what it says that if there exist two different spanning trees of a connected graph, then if you remove an edge from a particular graph, from a particular spanning tree T, then that particular tree will become disconnected. Why? Because every edge is a cut edge, that we have seen in the previous theorem. So the graph becomes disconnected, but another spanning tree T prime will have an edge E prime, basically, which connects these two disconnected components after removing E. Hence, after adding that particular E prime, the total graph, that is the total tree T minus E plus E prime, will become a spanning tree of G. So let us take the example before we go ahead about proof. So there are two trees, one is shown by the red, the other tree is shown by the green color. Let us assume that this is T, this is T prime. So if we remove this particular edge, so this particular tree with the red color will be disconnected here. But if we add another edge E prime, which is out of the another tree, then the entire graph again can be connected one. These two components will be connected. Let us see the proof by this particular corollary. By corollary 2.1.5a says that every edge of T is a cut edge. That is quite obvious. So when we remove an edge E, then let us assume that there are two disconnected components U and U prime. When that particular tree will remove this particular edge. Now since T prime is another spanning tree, so T prime is connected, so T prime has an edge E prime with an end vertices in U and U prime. So that means from T minus E, if we add an edge E prime, then this particular graph will be connected one, and also it has n minus 1 edges. Why? Because one edge is removed, one edge is added, so the number of edges is n minus 1, still the graph is a spanning tree. So another proposition says that if T and T prime are the spanning trees of a connected graph and E is an edge which is there in T but not there in T prime, then there is an edge E prime which is there in T prime but not there in T, such that in T prime if we add an edge and then remove an edge from T prime, then it will become a spanning tree. So T prime, if you add an edge, it will become a cycle, that you know that we have seen in the previous corollary, that in a tree if you add an edge, it will result into an exactly one cycle. Let us say that this cycle is C. Now since T is acyclic, there is another edge E prime which is there in the cycle but not there in that particular tree T. Hence, if we remove that, E prime will break only the cycle in T prime plus E. Hence, T prime plus E minus E will become connected and acyclic and is also a spanning tree of that particular graph G. Another proposition, if T is a tree with the k edges and G is a simple graph with little delta, that is the minimum degree is at least k, then T is a subgraph of G. So this particular proposition can be proved with the help of induction on k. When k is equal to 0, then every simple graph contains k1. K1 means isolated vertex is a k1, which is only a tree with no edges. So hence the base case is proved. Now induction means we assume that this particular induction hypothesis says that if for k greater than 0, let us say it holds. So we assume that the claim holds for the trees with a fewer than k edges. Since k is greater than 0, lemma 2.1.3 allows us to choose a leaf V in T. let u be its neighbor. Consider the smaller tree T prime, which is obtained by removing a particular vertex V, and so by induction hypothesis the smaller tree T prime, so G contains that smaller T prime as a subgraph. So this particular induction hypothesis, since this particular little delta of G is greater than K and K is basically greater than K minus 1. Now let us go ahead to prove this particular induction step. Since let X be the vertex in this copy of T prime here that corresponds to U, because T prime has only K minus 1 vertices other than U, and the degree of X is greater than K, that we have already seen. So X has the neighbor Y in G that is not in this copy of T prime. Adding an edge xy will expand this copy of T prime into a copy of T in G with Y playing a role of V. Hence this particular condition in the sense this induction is proved for a bigger values. Distance in trees and graphs. When using graph to model the communication network, we want vertices to be close together to avoid the communication delay. We measure the distance using the lengths of a path. Distance in trees and graphs. So if G has UV path, then distance from U to V is written as d of UV is the least length of UV path. If there is no such path exists, then this particular distance will be very high value, that is infinite. The diameter of a graph G is nothing but a maximum of the distances between any two pair of vertices, and that is the maximum of DUV available. So that becomes a parameter of the graph, diameter of a graph. So upper bound of the distance between any pair of the vertices. Similarly, eccentricity of a particular vertex is written by epsilon u is nothing but the maximum distance from that particular vertex to any other vertex. That becomes an eccentricity. So the radius of a graph is the minimum eccentricity, and similarly the diameter of a graph also we can say that the maximum eccentricity, which is there in the graph. So diameter equals the maximum of the vertex eccentricities. So in a disconnected graph, the diameter and the radius are infinite, because the distance between vertices in different component is infinite. The word diameter is used due to its use in the geometry, where it is the greatest distance between the two elements of a set. So let us take this particular example. So this is the graph, and if we calculate the distance between any two pair of vertices, what we find is that this particular distance is the maximum. So the diameter of this particular graph will become 3. Eccentricities, if we calculate, the minimum eccentricity is 2, so that becomes the radius. Similarly, the maximum eccentricity is 3, so diameter of a graph will become 3. The Peterson graph has the diameter 2, since non-adjacent vertices have a common neighbor. The hypercube QK has the diameter k, since it takes k steps to change all the k coordinates. Cycle Cn has the diameter n by 2. In each of these, every vertex has the same eccentricity, and the diameter of G is nothing but the radius of. For n is at least 3, the n vertex tree of the least diameter is the star with the diameter 2 and the radius 1. So you can see this is the star between any two pair of vertices the maximum distance is 2. So, the diameter of a star is 2. Now, as far as the radius is concerned, for this particular vertex, the distance is 1. So, that minimum eccentricity is 1. So, radius will become 1 in here in this case. Now, every path in a tree is the shortest, the path between its endpoints. So, the diameter of a tree is the length of its longest path. So, path is a tree. In this example, we can see the diameter is 4, radius is 2, and the length of the longest path is 7. So, length of a longest path, you can see 1, 2, 3, 4, 5, 6, 7. Theorem: if G is a simple graph, then diameter of G is at least 3. This will imply that diameter of the complement of G is at most 3. Proof: when diameter of G is more than 2, there exist a non-adjacent vertices U and V with no common neighbor. Take this particular example. This is U, this is V. So, they have this diameter is greater than 2. So, there will not be a common neighbors. So, there is no common neighbor of U and V here in this case. Why? Because it has 2 neighbors. Now, hence every x, if we remove U V, has at least one of these U and V as the non-neighbors. So, here this x will have V as a non-neighbor. So, that is what is stated over here. This makes x adjacent in G complement to at least one of U and V in G complement. Since also U V has an edge in G complement for every x y, for every pair x y, there is an x y path of length at most 3 in G complement through U V. Hence, the diameter of G prime is center. Definition: the center of a graph G is the subgraph induced by the vertices of minimum eccentricity. So, the center of a graph is the full graph if and only if the radius and the diameter is equal. So, take this particular example. Here in this particular graph, the radius is equal to the diameter. Then the entire graph will be the center of a graph. Is G. Now, in these examples, the vertices with the minimum eccentricity is this vertex, in this particular case here in this vertex, and here there are 2 vertices with a minimum eccentricity. Hence, this is an edge which will be the center. Similarly, here there will be a single vertex. Now, that there is a theorem, center of a tree is a vertex or an edge. So, the proof, we use the induction on the number of vertices in a tree. So, basic step, base case, when the number of nodes in a tree is at least, so at most 2, that means 2. So, with at most 2 vertices, the center will be the entire tree. Why? Because eccentricity of both the nodes are the same. Now, let us assume that the induction holds true for the number of nodes which are more than 2. Now, form T prime by deleting every leaf of T. By lemma 2.1.3, after deleting the leaf, the remaining, after deleting a leaf from a tree, the remaining tree, that is T prime, will also be a tree. since the internal vertices on the path between the leaves of tree remains. Why? Because only the pendant vertices will be removed, so internal nodes comprising that particular path will remain. So T prime has at least one vertex. Then every vertex at the maximum distance in T from the vertex U of that particular tree is a leaf. If not, then it will complete a cycle. That means the maximal path property. Since all the vertices, since all the leaves have been removed and no path between two other vertices uses the leaf, hence the eccentricity of the remaining tree, that is T prime, will be reduced by 1 for every vertex which is present in T prime. Also, the eccentricity of the leaf in T is greater than the eccentricity of its neighbors. Therefore, the vertices minimizing that eccentricity here for that particular vertex are the same as the vertices which will minimize the eccentricity here in T prime for those set of vertices. Thus, we have shown that it is shown that T and T prime have the same center by induction hypothesis. So, let us assume here that this is a tree. If we remove these particular vertices, they are called leaf vertices from T, then it will become T prime. In T prime also, if we remove these leaf nodes, then the remaining tree will be T double prime. So, T double prime will also be a tree, and so we keep on doing this iteratively till we form a T prime, so that either it will remain a vertex or an edge. Hence, this particular theorem is being proved. So, conclusion: in this lecture we have discussed the fundamental properties of trees and the distances in the trees and the graphs, and also discussed the theorems and lemma based on trees and distance. The upcoming lectures we will discuss spanning trees, enumerations, optimizations of trees. Thank you.